You know, your body is constantly sending signals to your brain, everything from the soft brush of a sleeve to the sharp sting of a paper cut. But how on earth does your brain tell the difference between those sensations and do it instantly? Well, the secret lies deep inside your nervous system, in a design that uses specialized pathways for very different kinds of information. Think about it. That difference between a gentle touch and a painful one feels immediate. It's just there. You don't have to analyze it. And it's not just that one signal is stronger than the other. It's like they're speaking two completely different languages. The key to how your brain is such a great translator is hidden inside your spinal cord. That's really the best way to think about it. Your body has these two distinct superhighways to get sensory information up to the brain. Each highway is built for a different type of traffic, making sure the right signals get to the right place right on time. And understanding these routes, well, that's the key to understanding how we perceive our world. All right, so let's pull over for a second and take a look at the map of these two highways. On one side, you've got the express lane, built for high-definition detail. And on the other, you've got the emergency route, reserved for urgent warnings. So first up, we have the Dorsal Column Pathway, or DCML for short. This is our fine details highway. It handles things like feeling the texture of a fabric, the vibration from your phone, or just knowing where your feet are without having to look down. Then we've got the spinothalamic tract, or STT. This is our warning signs highway, carrying the alerts for pain, temperature, and just that basic sense of being touched. So let's jump into the fast lane and take a ride on that first superhighway, the dorsal column. This is the pathway that gives us our most sophisticated, high-resolution sense of touch and body awareness. And the precision here is just incredible. The DCML is what allows for two-point discrimination. That cool trick where you can tell if you're being touched by one pin or two pins really close together. It also carries proprioception, which is your brain's internal GPS for your body parts. That's how you can touch your nose with your eyes closed without poking yourself in the eye. So what makes this highway so fast? What's its secret? Well, it uses the nervous system's version of fiber optic cables. These are huge nerve fibers wrapped in a fatty insulation called myelin. That insulation lets the signals just leap down the nerve at incredible speeds. It is a true express route to the brain. Okay, this next part is absolutely critical to understanding everything that comes next. It's all about the route. A signal, let's say from your right hand, travels up the right side of your spinal cord, all the way up. It doesn't cross, it stays on the right side until it gets way up high into the brainstem. It's only there, in a place called the medulla, that it finally crosses over to the left side of the brain. Seriously, burn this into your mind. It crosses over late and high. This is going to be a huge deal in a few minutes, trust me. All right, time to switch lanes. We're getting off the express route and merging onto our second highway, the spinothalamic tract. This one isn't about pretty details. This is the emergency lane. It's built for one thing, delivering urgent, non-negotiable warnings. Now, this highway has a couple of lanes itself. The main one, the lateral STT, is totally dedicated to those critical sensations, pain and temperature. The other one, the anterior STT, handles more basic stuff like crude touch, just knowing you're being touched, and firm pressure. And remember, those super fast fiber optic-like cables from the DCML? Well, the STT uses something different. It uses smaller, slower nerve fibers. So the signal itself isn't as zippy, but you know what? It doesn't need to be. The message it's carrying, pain, is a message that gets your attention no matter what. And here it is. This is the single biggest difference between our two highways. It's the whole ballgame. A pain signal from that same right hand comes into the spinal cord and bam, it crosses over to the left side almost instantly, right there on the spinal cord. It doesn't wait to get to the brainstem. It crosses low and early, then travels all the way up the opposite side. This immediate crossover is a total game changer. So you might be thinking, okay, one crosses high, one crosses low. Who cares? Well, this little detail about where they cross matters a ton because it explains some of the most bizarre and specific symptoms that happen when the spinal cord gets injured. And the classic textbook example of this is a condition called Brown-Séquard syndrome. This is what happens when exactly one half of the spinal cord is damaged, say the right half but not the left. What's so fascinating is that the strange pattern of what a person can and can't feel tells you exactly how these two highways are wired. Okay, let's break this down, because it's a little wild. If you have a lesion on the right side of your spinal cord, you lose fine touch and vibration on the right side of your body, the same side as the injury. Why? Because those DCML signals were still traveling up that side and hadn't crossed yet. But you lose pain and temperature sensation on the left side, the opposite side of the injury, because those STT signals had already crossed over way down low and were traveling up the now damaged right side. It's this bizarre, counterintuitive result that perfectly proves the two highways have different routes. Okay, that's damage to one half of the cord. But what if the damage was even more specific? What if it wasn't the whole side of the highway, but just a single critical intersection, right in the middle where those pain and temperature fibers are crossing over? Well, that exact scenario happens in a condition called syringomyelia. Basically, a fluid-filled cyst forms right in the center of the spinal cord and starts to expand outwards. And because of where it starts, the very first thing it hits are those crossing fibers of the spinothalamic tract. It's like a sinkhole opening up right in the middle of that critical intersection. And the result is one of the most unique patterns in neurology. The person loses pain and temperature sensation on both sides of their body, but only at the level of the cyst. This often creates a cape-like pattern of numbness across the shoulders and arms. But here's the kicker. Because the dorsal columns are way in the back, they're untouched, so fine touch and vibration are perfectly normal. Think about that for a second. You can feel a feather, but you can't feel a flame. It's wild. Okay, so just when we think we've got it all neatly mapped out, DCML for touch, STT for pain, simple, right? Well, science loves a good plot twist. It turns out our fine details highway has a secret side hustle. For decades, this division was basically gospel in neurology textbooks. The common wisdom, as this quote suggests, was that the dorsal column just didn't do pain, period. And here's the twist. Recent research has shown that the dorsal column is actually a major player in transmitting visceral pain. That's that deep, aching, hard-to-pinpoint pain you get from your internal organs. This discovery has completely changed how we think about things like chronic abdominal pain. And it's not as simple as just sending a signal up. It's more like this complex feedback system and amplification loop. The visceral pain signal goes up the dorsal column, the brain gets it, and then it can send signals back down to the spinal cord that essentially crank up the volume on that pain. It can become a vicious cycle. All right, so we've journeyed down these two sensory superhighways. We've seen the chaos that ensues when they get damaged, and we even uncovered a secret detour. What's the big picture here? Well, it's a story of an incredibly elegant, efficient, and surprisingly complex design. So let's recap. We've got two main sensory highways, the speedy DCML for all the fine details, and the STT for the urgent warning signs. The absolute key difference is where they cross over to the other side. The DCML does it high up in the brainstem, and the STT does it immediately in the spinal cord. This one anatomical fact explains all those weird patterns of sensory loss in spinal injuries. And of course, the system is always more complicated than we think, with the DCML moonlighting as a carrier for visceral pain. Which really leaves you with this big, fascinating question, right? Why? Why go through all the trouble of building two completely separate systems? It seems to tell us something profound about how our nervous system prioritizes information. Maybe it's all about an incredible evolutionary balancing act. One system designed to give us a rich, high-definition experience of the world, and another, more primitive system built for one simple purpose: keeping us alive.